Hello, Professor. This is Jeff Sexton. I'm going to go through the probabilities learning sheet. Let's take a look at what we have here. First off, we wanted to talk a little bit about probabilities themselves. We were given a data set here, and we're asked to give the probability of the A, what that probability is to come up within the set. We had 30%, 60%, and 60% for that C tabulation. We had to explain the function indicator x of A. If in there, we're asking how many of x is within the data set A. So if you do have one, you will get a 1 scenario. If you do not have that x in that subgroup A, we'll get a 0. So that's a good way that we have been using to go ahead and give our probability function. From here, we asked to explain a probability indicator. This is a summation set with k equal to 1 of n terms. We're looking at the indicator of x sub k of A. So we're asking how many x's in the set of A. We're asking for the kth term in this calculation. Likewise, for our frequency, we're asking for the frequency of x sub k of the set of x. That is going to be the frequency of the x in sub x, in the set x of the kth term again. And k in this point was 1, so the first term in that scenario. Summation of indicators. Wanted to go about and see if there's no overlap. How would you go ahead and tabulate the set of two different functions or two different sets of numbers? So x of A plus x of B is going to be the union x of the union of A and B. The next one, we were talking about the probability of A and X, and we're adding that to the probability of B and X, and that was going to be your probability of A, the union of A and B within the data set X. On L6, we're asking the sum of probabilities again, so pretty similar here. Going to be the probability of A union B of X in this scenario. We're going to subtract that from the probability of A intersection of B of X, and that's going to get rid of the overlap within that function itself. So if you have to get rid of overlap, that would be the scenario to do that. From here, we're giving a probability of A of the x given y set. So here's your x set, here's your y set, x given y is going to be that function that we've been using in live math. From here, I've done these in live math ahead of time, make sure these were correct. The probability of 2 or 3 being within the set of y is going to be 4 out of the 5. Within here, we're going to have another 4/5 and the 1/5 function. As you can see here, A of 4, 5, and 8. We only have one 4, so that's all we're looking for. There's only one 4 in that set. So of that set of the 2, 3, 4, 2, 3s, and 4s, 1, 2, 3 3s, and a 4, you have 5 data points. Of that 4, 5, and 8 set that we're asked to find the probability of x given y, there's only one number, that 4, that is going to be in the set y of sub x, given the A. That's 1/5. So that's how you do that one. We're looking at dice games now, which is another thing that we played a little bit into in the probability set. Given the 9s, 10s, and 11s, and 12s, you're going to have 10 different possibilities there. We said that given a random roll of greater than or equal to 9, you can see the probability of a roll of 10 is going to be 3 out of 10. So I did that probability there. Your A is going to be equal to your 10. You're looking for the 10 points out of this set. You could make your A 10 and 2, 3, 4, 5, you can get crazy with that if you wanted to, but really we're just looking for those 10 figures within the set given. Set given is going to be your x given y set, so your probability of A given your x given y set is again going to be 0.3 or 3 out of 10. Looking at independence, x and in the set x, two events A and y in x, how do we determine the independence of A and y? So we're looking at this a little bit more in detail. We're saying that the probability now of y and the probability of A within set x, both in this case happen to be for the given scenario of y equals 1 and 2, A equals 1 and 3. Both these probabilities of being within set x, 1, 2, 3, 4, is going to be 1/2. 1 half, and 1 half. So to determine here, we went ahead and said the probability of A and the probability of Y, we multiply the two of them to get a quarter. That quarter is going to be the probability of A union Y, X intersect Y. So it's going to be an independent event, and that is going to be our formula that we're given. The probability of A times the probability of Y is going to be equal to the probability of A intersect Y of X. Likewise, down here we could see we had a similar scenario, but we're asked for a different data set, this time 1, 2, and 3, and 4, so there's no intersection here. We're asked if this is going to be independent or not. This particular one is not, because again, that probability function that we're given is going to be equal to probability of A in X given Y is going to be equal to the probability of A intersect Y of X over the probability of Y of X, which in this case is 0. There is no intersection point or shared mutual point over the probability of Y, which was 1. So again, we have our probability of A of X is 1 half times our probability of Y of X is 1 half is equal to a quarter, which was that same scenario and same function. However, that's not going to equal to the predefined criteria that we set up for ourselves. Data set in X and two independent of X, A and Y in X. We are giving that formula. This is a formula that we've used before. Probability of A of X times the probability of Y of X is going to be equal to the probability of A intersection of X. Same function up there. And for non-independent of X, again, we did this up here. These should be equal to, in the event that they're not equal to, that's going to be a non-independent. That's going to be a non-independent event when those two do not equal up. Going through in the independent components in series, this was a notebook without a video, so we had to go ahead and look through this guy ourselves. This was from our notebook as well, so knowing the probability of component 1 and component 2 was going to give us our component working for a year, which is 0.72 in this scenario. Likewise, from here we wanted to see about a failure point, and that failure here was 0.5. So we did see our individual probabilities of failure, and then our equation that we were given was going to be the 1 minus the probability of failure minus the probability of failure of 2 given the failure of 1, which is going to be equal to 0.955 in that scenario. Similar concept here, we're asking for kind of switching up the numbers a little bit here, looking at probability of 0.9 and 0.7 failures, and what we wanted to find here was going to be the probability of the system composed of both components wired in parallel will work for a year. Again, this is from our notebook, and we found that our probability of component 1 plus component 2 is going to be subtract that from the probability of 1 and 2. That would give us a 0.97 as your answer there. And again, the failure scenario, this time we changed it to 0.6 with a little bit different spin on it. 1 minus the probability of failure 0.1 times the probability of F2 given F1 is going to be 0.946, so a little bit lower of a point than we saw before with the added failure point. I'm going to do a second video to go over these L13 terms for you.